complex numbers. This will be an introduction, so this will cover a lot of the stuff on the ordinary level course, and then there'll be a separate video for the content that comes up just purely on the higher level course. So the first thing we kind of need to consider is, what are complex numbers? Where do they come from? What do they involve? And what should we expect when we deal with them? So we're just going to start off perhaps in like a very simplistic manner, but if we think about what is the square root of 4, okay, and this might be an overly simplified question, but we know that the square root of 4 is plus or minus 2, okay, because 2 squared is 4, and minus 2 times minus 2, negative times a negative is a positive, that would also give us 4. Same with square root of 9, that's going to be plus or minus 3. Square root of 16, plus or minus 4. And then finally, square root of 169, that would give us plus or minus 13. Okay, so what we can see from this, hopefully, is that if we square any number, whether it's positive or it's negative, the outcome will always be positive. All right, that's what we should hopefully be taking away from this. So negative times a negative is a positive, positive times a positive is also a positive. So where does that leave us when we have the square root of a negative number? If I said to you, what is the square root of minus 4? Well, we don't actually have any real numbers that can effectively describe that or quantify it for ourselves. So this is where complex numbers come into things. What we have here is what's called an imaginary number, okay? And the whole foundation for complex numbers is, it ties in very well with algebra, because what they're actually saying in complex numbers is that I, so this letter I, is equal to the square root of negative 1. Okay, and likewise, if we were to square both sides, obviously a square root and squaring are opposites, well then we would have that I squared is equal to minus 1. Alright, so this is where this whole chapter comes from. We had these square roots of negative numbers, and we just needed a way to describe them, quantify them for ourselves, and to answer questions based around these. So this is the whole foundation for it. What we see in complex numbers is actually that we have real numbers and they're being mixed with imaginary numbers. So complex numbers always come in the form a plus bi, where a and b are real numbers, and I is an imaginary number such that I is always equal to the square root of minus 1, or as we said a moment ago, I squared is equal to minus 1. Okay, so if we were just to pick a random example of a complex number, we could have something like 3 plus 2i. Okay, that's a complex number. We have our real element, 2 is a real element, and I would fall in line with these rules that we've discussed here. Okay, another example, 4 minus 3i, 6 plus 2i, and so on, minus 3, minus 4i, and such like that, okay? Alright, so we'll be asked to answer a number of questions on these. It's argued by a lot of people that this is probably one of the easier questions when it comes to certainly ordinary level Leaving Cert, because they tend to be repetitive, and we'll see similar questions year to year. So if you can kind of get into the habit of understanding these and answering these fully, it can often be an easy 25 marks to pick up, or even 20 out of the 25. Okay, so we're just going to move on now to looking at some sample questions. Okay, so we're just going to consider these things briefly here. We're not going to dwell too long on them. So what we're trying to look at here is we obviously have up top there square root of minus 4 and square root of minus 72. Is there any way to write these in terms of I? That's what we're going to think about right now. Well, there is. So we could break up that square root of negative 4, and we could break it up into square root of negative 4 times square root of negative 1, because when we multiply these two things out, we're going to finish with the square root of minus 4. Okay, now we know clearly that square root of positive 4 is going to be 2, okay, plus or minus 2, and we know that square root of negative 1 cannot be simplified any further, but we also know from Previously, that square root of negative 1 could be substituted for I, so this would become 2 times I, okay, and that's our solution to that one. Now, if we look at square root 72, so this one is slightly more complex, we have more steps to it. Let's try and simplify it in a similar manner. So let's take out square root positive 72 times square root negative 1. All right. Now, can we break down the square root of 72 any further? Well, we can. If we were to divide it by 2, let's say, that would give us square root of 36 times square root of 2 times our square root of negative 1. That remains the same. So I'm going to simplify this again a bit further. So we know that square root of 36, we could check it on our calculators, but hopefully it's something that we could do mentally, and we know that that's 6. So that's 6 times square root 2. We know that the square root of negative 1 can be represented by the letter I. So what this one actually is 6 square root 2I. Okay, that's that one simplified for us there. Now, if we think about these guys here, if we wanted to know if it was negative I or positive I, well, something that has been established for us is that I squared is equal to negative 1. Right? That's something that we discussed a few moments ago, and it's the whole foundation for what we are working with here. If we were to try simplify I cubed, now, we know that I cubed is I times I times I. Now I'm going to kind of group these guys together. I know that I by I is I squared, so it's I squared times I. Now I squared is minus 1. Let's substitute that in. So that's minus 1 times I. I can't simplify that any further. So what I have here is minus 1I, or just minus I. Okay. Now let's do the same thing here. If you want to pause the video and give I to the power of 4 a go. So what we have here is I to the power of 4 is the same as I times I times I times I. Let's group these guys together. We get I squared, okay, times I squared. I squared is equal to minus 1. So what we have here is minus 1 times minus 1, okay. It's pretty straightforward. We just subbed in minus 1 where we had our I squared. And what this will leave us with is minus 1 times minus 1 gives us plus 1. Okay, that is our solution there. So therefore, I suppose what we could say for this one is that I to the power of 4 is equal to positive 1. And over here, obviously, we would have I to the power of 3 is equal to negative 1. Okay, so the next thing we're going to look at is there any way to graphically represent our complex numbers? So we've kind of looked so far at imaginary numbers and the fact that they are derived from the square root of negative numbers. And we also discussed at the beginning that complex numbers are a combination of numbers that we're familiar with, being real numbers, and these new imaginary numbers. So again, they always take the form of a plus bi, where a and b are real numbers, and I squared is equal to minus 1. And that'll always be presented to you in the question, that I squared is equal to minus 1. So obviously here on the left we have different complex numbers. So the first one there, 2 plus I, minus 1 minus I, 2 minus 2I, and minus 2 plus 1I. And over here on the right we have our axes. So it's kind of like coordinate geometry in a sense, in that we can graph these and we can use the information presented to us in the complex number to figure out where exactly it lies on our plane. Now the difference between this and complex number, or this and coordinate geometry, is that our traditional x-axis, so our horizontal axis, is our numbers, our real numbers. So our a value is on our x-axis, okay, our horizontal. And on our y-axis, or our vertical axis, we have the imaginary values, the I values. Okay, so we have I, minus 2I, and plus 1I. We will refer to our vertical axis when we want to plot those values. So in coordinate geometry, typically we see the numbers presented to us in the form of 2, 1 in brackets. So it's a little bit different here with complex numbers. They're not presented to us in that fashion. So if we were to think about our first complex number there, 2 plus 1i, or just 2 plus I, let's look at our horizontal axis first. So our value is 2, so it's going to be somewhere along here, okay? And then our I value is just 1i. So if we were to go ahead and plot that, we would find that it's right there, okay? It's at that point. That is the complex number 2 plus I, and it has been plotted. All right. Okay, perfect. And our next complex number here, the second one, we have minus 1 minus I. All right, so let's use our horizontal axis for the minus 1, the A value. So that's going to be somewhere along here. And then our minus I, so now we refer to our vertical axis, or what we would traditionally see as our y-axis, and we would have minus 1 minus 1i, or minus I, so that will lie there. Okay. Next up we have 2 minus 2i, so again we go back to our horizontal axis for our a value, which is 2, somewhere along here, and now we go to our vertical axis for our minus 2i, so we can see that that complex number, if we were to plot it, is right there. Okay. And finally, our last one now, we have minus 2 plus I, or minus 2 plus 1i. So our A value, we go to the horizontal axis, and that is minus 2. It's somewhere along here. And then we have plus 1i. So vertically, we're going to go up to plus 1i. So that would be plotted just there. Okay, so that is the plotting of our complex numbers, and what we call this here is an Argand diagram. So it's a very specific way of plotting complex numbers. It does have some similarities with coordinate geometry and plotting points in that respect, but our axes are labeled a little bit differently. So often what we'll see throughout complex numbers is that complex numbers are labelled using Z. So here we can see we have the complex number 2 plus 3i, and we're just calling that one Z1 for now. Just another way of referring to it. And we also have the complex number 1 plus 5i, and we're going to label that as Z2, just a way to refer to it. And we're going to see how these guys work for addition, subtraction, multiplication, and then we'll move on to division a short while after. So it's very similar to algebra in a sense. Like if we think about algebra, if we had an expression that was 2x plus 3y plus 4x minus 1y. Well, hopefully what we know about this is that our similar terms can be combined, and that means that we can't have 2x plus 3y because they're just different. They have different variables and they don't mix well together. So we need to make sure that our x's go with our x's and our y's go with our y's. So 2x plus 4x, well, that would give me 6x, and then we have 3y, take away 1y, that would give me just 2y. And that is my solution to that problem there. And it's very similar here when it comes to complex numbers. I'm going to write out our Z1 plus Z2. So Z1 is 2 plus 3i as we established. Okay. Plus Z2, which is 1 plus 5i. Alright. So again, it's like with like. I'm just going to pull away those brackets. So we have 2 plus 3i plus 1 plus 5i. Okay, so 2 plus 1, well, that's going to simplify to 3. That's pretty straightforward. And then we have 3i plus 5i, that simplifies to 8i. And that is my solution there for that question. I don't need to take it any further. That's as simple as I can get it. I have added those two complex numbers together. And the important thing is that the i's went together and our real number, or our a value, also went together. So now, if we are to consider the subtraction, so I'm just going to write this out in long form. So we have 2 plus 3i, okay, minus 1 plus 5i. Okay, I'm going to pull away these brackets. So my first one stays the same. It's 2 plus 3i. Now I need to consider this negative sign here. So it's almost as if there's a 1 here being multiplied in. So minus 1 times 1 would give me minus 1, and minus 1 times plus 5i would actually give me minus 5i. So it's very important to watch out for those signs when it comes to dealing with our brackets. And now I can do this question the exact same as I've done this one here, like with like. So 2 minus 1, well, that just gives me 1. And then 3i, take away 5i, well, that gives me minus 2i. Okay, and that is my solution to this question here. So we can see that it's very similar to algebra in the sense that like goes with like. Okay, I didn't combine real numbers there in terms of 2. I didn't try and add that to 3i and see where it got me, because they're just different. They can't work with each other in that respect. Okay, so we're going to keep our z1, z2 the exact same for this question here. z1 again is equal to 2 plus 3i, and z2 is equal to 1 plus 5i. So first of all, we're going to consider what happens a complex number when we multiply it by a real number, the real number here being 2, of course. And then on this side of the sheet, we're going to look at multiplying those two complex numbers by each other. Alright, so let's consider this here. We have 2 times 2 plus 3i. And when it comes to multiplication, we're not posed with as many problems in terms of having like go with like as we saw with our addition and subtraction problems. So for this one here, it's just a case of multiplying our 2 in evenly. So 2 times 2 is 4, and 2 times 3i is plus 6i. Alright, and that is our solution to that question there. Straightforward enough, no big problems. Of course, when it comes to real numbers, that could be a minus 6, it could be a plus 100. It can vary quite a bit as to what we are multiplying in. And now we come to our complex numbers multiplying by other complex numbers. So I'm going to write this one out in our brackets. We have 2 plus 3i, okay, times 1 plus 5i. So this is kind of like our binomial expansion, expanding out 2 brackets as we would have seen in early algebra and quadratics. So there's a number of ways of doing this. We can use the box method, the array method, but probably what's most straightforward just in terms of this explanation is multiplying the 2 brackets together and expanding them that way. Okay, so making sure that everything is multiplied by the 2 values in the other bracket. So we'll start off with our 2. So 2 times 1 is 2. 2 times 5i is plus 10i. 3i times 1 is plus 3i. Okay, and then we have 3i times 5i. So 3 times 5, that would give me 15. And then we have our I times I would give me I squared. Okay, so I've expanded it out. It's now time to tidy it up. So again, now we kind of have our addition and subtraction evident in front of us here, and again we go like with like. So at the moment our 2 is going to stay as is. 10i plus 3i, well, that would give me 13i, yeah? And then we have a plus 15i squared. So as we've spoken about throughout this topic, what we see is that I squared is equal to minus 1. And we have that noted in all of our questions. It'll be in the description at the top. So now let's substitute in minus 1 instead of I squared. See if we can make our lives a little bit easier. So what we have there then is plus 15. Now instead of I squared, we have minus 1. Let's try simplify this a bit further. We have 2 plus 13i. 15 times minus 1, well, that gives me minus 15. And I can simplify this one final step. I have 2 take away 15, well, that would give me minus 13 plus 13i. Okay, and that is my solution to this problem here. So as we could see, multiplying by a real number is typically a little bit more straightforward, and multiplying 2 complex numbers, that's where things can get you know, a little busier. But if we're tracking things properly and we're using all of our rules that we discovered in algebra properly, it shouldn't pose too much of an issue for us.